Hi students, in today's session what I'm going to do is solve the book back exercise of the chapter Thermodynamics from class 11 chemistry. So in the first part I have discussed the concepts up to work done and internal energy. In today's class what I'm going to teach is the concept, a new concept, enthalpy and heat capacity, and I'm going to solve the book back exercise numericals based on these concepts. Okay, so first of all, what is enthalpy? So it is a new thermodynamic state function. Okay, so which is change in the enthalpy. Okay, actually this does not differ much from your change in internal energy. Okay, there is no significant difference between these two terms for the systems involving solids and liquids, because the systems involving solids and liquids, okay, so in these kind of reactions there will not be any significant compression or expansion that takes place. There is no significant change in the volume here. Okay, so your change in internal energy is equal to the change in the enthalpy. Okay, so for solids and liquids there will not be any considerable change in the volume, but for gases, if you take, see, there will be, if you deal with these systems, there will be some compression, or else expansion during dealing with the systems containing gases. Okay, so there will always be a pressure volume work done, which is work, pressure volume work done, which is nothing but work. Okay, so you have to consider these work done while calculating your enthalpy. So you have to sum it up with your internal energy. So this is for your gaseous molecule. So from your ideal gas equation, so we can write this as your del H is equal to del U plus del Ng RT. Okay, so this is a very important equation, students. So often more questions will be asked based on these questions, and these questions can be easily solved. Okay, so here this is your change in enthalpy, change in your internal energy, and what is del Ng? Okay, so it is the difference between the number of moles of gaseous products, okay, minus same number of moles of gaseous reactants. That's all. So when we solve the problem, when we do numericals, you will actually get to know, okay, what it is. Okay, so this is what number of moles of gaseous products minus number of moles of gaseous reactants, where R is equal to your gas constant, which is 8.314 joules, okay, per Kelvin per mole. Okay, so this is very important, where T is your temperature in Kelvin, where T is the temperature in Kelvin. Okay, so this is a very important equation which we are going to use it, okay, while solving the numericals. One thing I want to tell you, see here, you know that your change in internal energy is what? It is nothing but your heat and your work done. It is the summation of heat and work done. See what happens at constant volume, students. At constant volume means there is no change in volume. Your volume remains constant. So we can say that your del V is equal to 0. But we know that your W is equal to minus P del V. When your del V becomes 0, your work done will also becomes 0, isn't it? So what happens to your internal energy at constant volume then? So Q plus 0, so at constant volume, your change in internal energy is equal to QV. This subscript V is to represent it takes place at constant volume. Okay, so please remember this. So whenever I box it, no, the formula, you have to write it separately and revise it. Okay, only based on those formulas you have to do the numericals. If you know all the formulas, thermodynamics is nothing. Okay, so I'm not going to do any derivation here. Similarly, your enthalpy, so this is at constant pressure. So if at constant volume your del U is equal to QV, at constant pressure your del H is equal to QP. Okay, so please remember this. Okay, then I'm going to tell you another concept, which is your heat capacity. Okay, now it is a time for heat capacity. It is it is represented as C. Okay, so what is heat capacity, students? See, suppose when you have taken a vessel of water, okay, you started supplying heat to it, you started heating it, okay, and your thermometer has been inserted to measure the temperature. So what do you observe? Soon after you started heating, will there be any rise in temperature? It takes some time, isn't it? It takes some time to till you see any rise in temperature in the thermometer. Okay, till that point, what happens to the heat that you supply to the water? Okay, have you ever thought about that? So the heat being observed, isn't it absorbed by the water, then the excess heat which could not be absorbed by the water is only giving rise to the temperature, increase in temperature. Then only we will see the rise in temperature after a certain time. Okay, so the heat that has been absorbed by water is the heat capacity of water. This is a example I have taken. So similarly, each and every material, if you take copper, if you take any metal, any material will have their own heat capacity. Okay, it is if the heat capacity is more, then you have to supply more energy, more heat to bring that to a higher temperature, isn't it? So water's heat capacity is more, so you have to supply more energy to make the water boil. Okay, so now the heat capacity, we have a formula. See, we can say that the amount of heat can be measured by the product of the heat capacity, okay, and the change in temperature. Okay, so the product of the heat capacity of the material multiplied by the rise in temperature, you can actually measure the amount of heat that you have supplied. Okay, so Q is equal to C into del T. This is the change in temperature and this is the amount of heat you have supplied, and this is the heat capacity of a substance to which you are passing heat. So this heat capacity, okay, can be or of two types. See, this is molar heat capacity and specific heat capacity. Molar heat capacity is represented as Cm. Okay, so what is molar heat capacity? It is the quantity of heat needed to rise the temperature of 1 mole of the substance. Okay, 1 mole of the substance, okay, by 1 degree Celsius. Okay, so you have to supply heat, okay, to make 1 mole of the substance to 1 degree Celsius, that much amount of heat. Okay, so heat capacity, what is specific heat capacity? It is the quantity of heat needed to rise the temperature of 1 gram of the substance. What is the difference here? It is 1 mole and it is 1 gram, okay, of the substance by 1 degree Celsius. So your Cm is nothing but your heat capacity divided by number of moles. Okay, what is your Cm? So it is the heat capacity. When you divide the heat capacity by the number of moles, okay, you will get the molar heat capacity. So here we know that Q is equal to C multiplied by change in temperature. So at constant volume, you can write QV is equal to CV multiplied by del T. Okay, and similarly at constant pressure, QP is equal to CP into del T. Okay, so this suffix P is to represent that the reaction is taking place at constant constant volume and constant pressure. Okay, so we know that what it is, your del U is equal to QV, isn't it? So we can write that del U is equal to CV into del T, and your del H is equal to QP, isn't it? So I can write del H is equal to CP del T. Okay, sometimes I am writing this multiplication symbol and sometimes I am not. Okay, that doesn't make any difference. Okay, students, please don't confuse yourself. So these are the important formulas that you have to know to solve the numericals, okay, in today's session. Okay, so please take a note of it. Okay, so solving your book back exercise. So I am writing the corresponding question number here, students. So this is the book back exercise 6.1. See, the standard change in internal energy of combustion of methane is minus x kilojoules per mole, the value of del H. See, if they are asking, see, relating del U and del H, what formula you have to choose? You have to choose the formula del H is equal to del U, okay, plus del NGRT. Okay, so methane is CH4. So some formulas you have to remember. See, combustion they have written. What is combustion, students? So combustion means reaction with oxygen. Okay, so reaction of oxygen, how to write the formula? See, convert all the carbon to carbon dioxide and hydrogen to water. That's all. Then balance the equation. This is the combustion equation of methane. Okay, so here one carbon and 4 hydrogens are there, so I'm putting here 2, and oxygen, what is the number of oxygen? So here this is the balanced equation. Okay, so what you have to do write the correct equation and balance those equations. So here we know that methane is gaseous in nature and oxygen is gaseous in nature, and carbon dioxide is also gaseous in nature, and water, usually liquid water, will be produced in the reaction. Okay, so now what you have to do for this, since you have to use this equation, you need to know this term. Okay, so your del Ng, what I said, del Ng is the number of gaseous products minus number of gaseous reactants. How many gaseous products are there? There is only one. Okay, so you have to see the stoichiometric ratio here stoichiometric coefficient here. So this is 1, and here this is also a gaseous molecule, this is also gaseous molecule. Okay, 1 plus 2 is what? 3. Okay, number of gaseous product is 1, gaseous product is 1, gaseous reactants are 3 here. Okay, so the del Ng value 1 minus 3 is minus 2. Okay, let's substitute in this equation. Okay, so your del H is equal to, del value is given, that is minus x. Okay, minus x. So then plus del Ng is what? You got minus 2. Okay, RT. Okay, so here this is what you can simply substitute del U itself minus 2 RT. Okay, so here your enthalpy is your internal energy minus some amount. Okay, if you subtract this quantity from your internal energy, you will get enthalpy. Okay, then what option will come, students? So enthalpy will equal to internal energy? No, it is not equal. Okay, it is greater than internal energy? No, it is not greater than internal energy. You have to subtract a term from the internal energy. So I can say your internal energy, your change in enthalpy is lesser than your change in internal energy. You got my point, students? If only you subtract this quantity from this, you are getting enthalpy. So the resulting amount must be a smaller amount than your internal change in internal energy. So the option is third one. So next question, the reaction of cyanamide, and this is your 6.8 question from your book back exercise. Cyanamide with dioxygen was carried out in a bomb calorimeter, and the internal energy was found to be this much kilojoules per mole at 298 Kelvin. Calculate the enthalpy change. Okay, so here also they have related your del U and your enthalpy. Okay, so which formula you have to use, students? You have to use your del H is equal to del U plus del NGRT. Okay, so this is the equation. So this is your reactant side and product side. So to calculate del Ng, what you have to do? To know the number of gaseous molecules here. See, here 1 and here 1, the gaseous molecules, and this is liquid. Okay, so here totally 2 gaseous molecules are there, and here there is 1 and 3.2, 3 by 2. Okay, so 1 plus 3 by 2, what, students? So here it is what? If you add, it is 5 by 2. Actually it is what? 2.5, isn't it? 2.5. So your del Ng is equal to number of gaseous products minus number of gaseous reactants. So 2 minus 2.5, which is minus half. Okay, which is minus half. Okay, why I am writing minus half is for the calculation purpose. So the del H is equal to del U. I am taking this value. Okay, I am taking this value. So minus 742.7. Okay, so minus half. Okay, minus half into 8.314. And one more thing, See, this is in kilojoules, isn't it? But your R value is in joules. Okay, so what we can do is you convert this kilojoules into joules by multiplying 10 to the power of 3. Okay, so into 298 Kelvin. Okay, so if you multiply this, so this is 742,700 minus, see what I'm going to do is, see we should not use calculator, isn't it? So I'm neglecting these decimals, so that will not create much difference in your answer. So 8 divided by 2 is 4. Okay, so if you multiply this 298 into 4, so if you do this, okay, you are getting not much from your original answer. So this is what in joules per mole. So the answer in kilojoules per mole is actually 241.5 kilojoules per mole. Okay, this is your answer. So next, the 6.9 question from your book back exercise. Calculate the number of kilojoules of heat necessary to rise the temperature of 60 grams of aluminium from 35 degrees Celsius to 55 degrees Celsius. Molar heat capacity of aluminium is 24. Okay, so molar heat capacity, what is Cm, isn't it? So that is represented as Cm, joules per mole Kelvin. Okay, so this question is related to heat capacity. So which formula you have to choose? So Q is equal to C into del T. Okay, so if you use this formula you will get, but your molar heat capacity is given. We know that molar heat capacity is heat capacity divided by number of moles, isn't it? So you can actually find the heat capacity by multiplying the given molar heat capacity, where n is the number of moles. How to calculate number of moles, students? So that is the given weight, isn't it? So given weight divided by the atomic weight. What is the given weight here, students? So given weight is 60 grams. 60 grams divided by 27 grams. So if you do this, you will get the number of moles. Then what is del T here? Del T is actually T2 minus T1. So the difference in temperature, 55 minus 35 is 20 degrees Celsius. Okay, so Q is equal to, I'm going to substitute all this amount. So Cm, what is Cm? So 24 joules. Okay, it is in joules. Multiplied by n. What is the value of n? It is 60 by 27. Okay, into 20. Okay, if you solve this, your answer will be, okay, 1.067 kilojoules per mole. Actually you will get before here 1067, okay, joules per mole. Okay, when you convert this into kilojoules, you have to divide by 1000, isn't it? Divided by 1000, you will get the answer in kilojoules per mole. Always remember, students, whenever you have to convert joules into kilojoules, okay, then you have to divide the joules by 1000. Okay, then you will get kilojoules. Okay, suppose you have to convert kilojoules to joules, you have to multiply this into 1000. Okay, you to get the answer in. See the question here, students, 6.10 from your book back exercise. This question actually appears to be tough, but actually it is not. You have to first understand the question, okay, slowly, then only and clearly. Okay, then only you can solve these kind of questions. See, calculate the enthalpy change on freezing of 1 mole of water at 10 degrees Celsius to ice to minus 10 degrees Celsius. Okay, and enthalpy of fusion value is given and some data have been given. Okay, so first clearly understand what they have asked and what they have given. See, there is a system. Okay, there is a system of water. Okay, so this is a liquid water. At what temperature it is? It is 1 mole of water. Okay, so it is 1 mole of water. At what temperature? It is 10 degrees Celsius. Okay, they are asking the enthalpy change involved, okay, to convert this water into ice. Okay, so it is now solid in nature. Okay, at what temperature? 10 degrees Celsius. So to convert the water at 10 degrees Celsius to the ice at minus 10 degrees Celsius, find the enthalpy. Okay, so please don't confuse yourself. So I will clearly explain how to solve this. See, the enthalpy involved in this entire conversion is, okay, so you have a liquid water, so this is 1 mole. Okay, each and everything is 1 mole, no doubt about this. So first, at 10 degrees Celsius water, you have to bring that water to 0 degrees Celsius. Okay, so here one enthalpy will be involved. Okay, then to convert this water into ice, so ice at 0 degrees Celsius. Okay, so here one enthalpy is involved. Then you have to convert, okay, bring this ice at 0 degrees Celsius to minus 10 degrees Celsius. So there are 3 enthalpies involved. Okay, so how to solve this step by step, I will tell you. So first calculate the del H1. Okay, so del H1, see, for this the datas have been given, I already told you. So this takes place at constant pressure, so you can use this. Okay, Cp del T, so your Qp is what? Del H. Okay, I already told you del H is equal to Qp. So del H1 is nothing but Cp into del T. Okay, so for this Cp of water, the heat capacity at constant pressure for the liquid water is given. Okay, so the liquid water, so here the temperature changes from, okay, 10 degrees Celsius to 0 degrees Celsius. So this is your T1 and this is your T2, isn't it? Your del T is what? T2 minus T1. So your Cp is 75.3. Okay, into what is T2? T2 is 0 degrees Celsius minus 10 degrees Celsius. Okay, so your answer is 75. Okay, 753. Okay, this is joules per mole per Kelvin. So you have found out del H1. Okay, so now what is it? Your del H2. See students, del H2, the liquid water at 0 degrees Celsius is converting to ice at 0 degrees Celsius. See this data. Okay, this data, enthalpy of fusion is given. Okay, enthalpy of fusion normally means the reverse. The ice is converting to liquid water, and this we call it as fusion. The ice converting to liquid, we call it as fusion. The enthalpy of fusion is 6.03 kilojoules per mole. Okay, so here what happens here? See, the reverse is going to happen. Liquid to ice at 0 degrees Celsius. So it is the reverse of enthalpy of fusion, isn't it? So the value here is minus 6.03 kilojoules per mole. You understand, students? So ice to liquid is enthalpy of fusion, its value is given here. Liquid to ice at 0 degrees Celsius. Okay, so it is a reverse of, so I'm reversing the value. Okay, it is a thermodynamic property, isn't it? So your del H2 is nothing but 6.03. See here the value is in kilojoules per mole. Okay, so it is in joules per mole, it is in kilojoules per mole. Okay, so to convert this, so what we can do, we can convert this into joules. So instead, so minus 0.753 kilojoules per mole per Kelvin. So the remaining thing what we have to solve is only the third enthalpy change. So here also ice is converting to ice, only the temperature is differing. Okay, here liquid to ice, liquid to solid. Okay, so here the same thing only, but temperature only differs. So we are going to use the formula Cp del T. Okay, so here this is the T1 here and this is the T2 here, and here the enthalpy, the heat capacity of ice is given. Okay, so use that. So here, so 36.8, what is T2? T2 is minus 10 minus T1. T1 is 0 degrees Celsius. Okay, so the answer is 36.8 minus 36.8 joules per mole per Kelvin. And if you convert this into so here convert this into kilojoules. So here it is. Okay, so the total enthalpy involved is equal to del H1 plus del H2 plus del H3, isn't it? So bring all the values here. So minus 0.753. So if you do these kind of problems, make sure the kilojoules and joules, everything, okay, all are in same units. Okay, so if you sum it up, your final answer is minus 7.151 kilojoules per mole. Okay students, so I'll meet you in my upcoming videos with the remaining concepts. Okay, thanks for watching.